Yo, 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 guys. Hey, let's jump into Chapter 19 content. And before I do this, I want to kind of give you a context. Rachel, this will be one part of the video where you're going to want to skip ahead because I'm not going to write anything down. I'm just going to talk for a little while. So anyway, Chapter 19 has us working sort of in the reverse from what we did in Chapter 18. In 18, primarily, actually all of the problems did this. We were given either a population proportion, and we wanted to learn about how samples would behave of particular sizes, or we were given a mean value, for instance, for people's heights, and then there too we wanted to look at how samples of a particular size would behave for mean heights or mean weights of people or mean GPAs, that sort of a thing. Well, Chapter 19 goes in reverse, and I think it's much more interesting statistics. Although, thankfully, the math is really no different at all. I'm not going to show you anything new math-wise, but the conclusions we're going to make are very different. So here, look at example 1 and what we've got there. That's going to be our segue here. May 2000 Gallup poll found that 38% of a random sample of 1,012 adults said that they believe in ghosts. Okay, so here we've got information about how a sample behaves. And naturally, I mean, as you guys, even before you came into this class, I'm sure some of you guys could intuit that when you conduct a sample, you really care to learn about how the larger population behaves. And those are the sorts of conclusions we're going to make in Chapter 19. For instance, not only, I mean, we obviously know that 38% of the 10,000 or 1,012 people believe in ghosts. What's going on with all of the U.S. adult population? All right, so let's go ahead and start writing some stuff down. We have given to us p hat, which in this case is the sample proportion of 1,012 adults believing in ghosts in the U.S. Leave I before E in ghosts. Okay, all right. So, well, to make conclusions about the population at large, we need to go through some conditions, just like we did last chapter. And our conditions here are basically identical to the conditions we had for a sampling distribution of proportions, but there's one new one. We need to look at the plausible independence condition, or just plausible independence. Okay, what does that mean? Well, this one is something that we've just got to kind of got to reason through based upon the context of the problem. Does it make sense to assume, in this case, that the responses of the people in the survey did not directly influence each other? I think, yeah, that's fair. Assuming that the Gallup poll was conducted in such a way that people were not like just in a line and there was the opportunity for peer pressure to arise, yeah, we can safely assume that these 1,012 people don't influence each other's responses. So, yes, we'll assume this has been met. Semicolon, people's responses shouldn't affect each other. Okay, so there's our new condition. And the other three, as you may remember, randomization was the first one that we checked. That is basically just saying, can we assume that the 1,012 people are an SRS, a simple random sample? So we are told that. We're told this is met. All right, so there's the second condition. Third condition here. We need to check the 10% condition, just like we did for sampling distribution of proportions. 10% condition. Well, Yeah, that's certainly met. We've got more than 10,120 people in the United States. So this is met by a landslide. There are more than 10,120 peeps in the Union, in the United States. All right, fourth condition, success failure. Okay, and here we're basically checking whether or not, just like in the past, do we have at least 10 successes? Do we have at least 10 failures in our sample? Yeah, absolutely. We got 1,012 people with a 38% probability of success, so to speak. For success, that's 0.38 times 1,012. Let me pull up my notes here to see what that comes out to be. That is approximately 385, which is certainly greater than 10, so that checks out. For failure, we're checking 0.62, the complement of the 0.38, times 1,012, which is approximately 627, certainly greater than 10, so that checks out as well. Okay, so the four conditions have been met to go ahead and build a normal bell curve. And shortly it'll start to become a little bit more interesting. So let me extend the page. We did the conditions. I call it, the book lays this sort of problem out differently than I do. In conditions, then mechanics makes sense, or guts, or the real math here. Mechanics. Okay, so we have the go-ahead because the conditions have been met to build a bell curve that models the sample proportions, how they would behave from sample to sample to sample. So this is the distribution of p hat for a title. The expected value of p hat is, well, I mean, we have p hat. We know what the sample proportion is. That's just 0.38. And when we concluded Chapter 18, I was telling you guys that if you don't have population proportions, you instead have sample proportions, you don't call the standard deviation. You call it the standard error. But it's calculated pretty much the same way. So the standard error of p hat is equal to the square root of, instead of pq over n, p hat, q hat over n, which is just the square root of 0.38 times 0.62 all over 1012. Comes out to be 0.015. Okay, so how do sample proportions of size 1012 from people in the United States behave? Well, from the proportion we have, we expect that generally they're going to be at 0.38, thereabouts. Not that exactly. This bell curve obviously takes on continuous values. 0.38 is, for samples to behave that way, that where we would see that sort of average, sample after sample, is just unfathomable. It could be 0.385, it could be 0.3805. There's basically a 0% probability that it would be exactly 0.38. But again, the bell curve says we expect that it should be close to that because of the height of the distribution around 0.38. All right, so to either side, one standard deviation out to the right and to the left, we have 0.395 and 0.365. Two out, we're looking at 0.41 and 0.350. Okay, so remember the 68, 95, 99, 7 rule. Well, what can we conclude? The bell curve that we built, if you remember from last chapter, says basically we expect that 95% of all sample proportions of size 1012 from U.S. adults in the population, did I say 68 or 95? 68% of them should fall within this range, and that 95% should fall within that range. Well, similarly, P, the true population proportion of people who believe in ghosts in the U.S., has to fall within those boundaries as well. Well, it doesn't have to, but is likely to. Should be careful there. It's likely to fall within those boundaries. So two conclusions that we can make here. The first We'll just call this A. First conclusion that we could make is that with 68% confidence, and all that I'm underlining here, we're going to not mathematically define that, but more rigorously show you what that means in just a second. For now, just think of it in sort of practical terms. With a fair amount of confidence, P, the true proportion of U.S. adults believing in ghosts falls between 0.38 plus or minus 0.015. So at 0.38, that's the expected value of a sample proportion, but one standard deviation out to either side, that's the 0.38 plus or minus 0.015. We expect 68% of all sample proportions should fall within that gap, that net. It's sort of a net that we're casting here. And similarly, P, the true population proportion of U.S. adults believing in ghosts, should fall within that boundary too. With 68% confidence, we believe that. Or we could say, less accurately, but more, we lose accuracy here, but we have more certainty. We could say with 95% confidence, I bet you can see where this is going, P, I'm not going to redefine that, so I don't need the comma, falls between 0.38 plus or minus, well, two standard deviations out to either side, gives us the 95% interval here. 0.38 plus or minus, the standard error, excuse me, is 0.015, and we're talking about 0.030, double the 0.015. So, the two things that I've just boxed for you are confidence intervals. That's the, and when you specify a confidence, you say the percent confidence you have in the interval. So with 68% confidence, we believe it could fall within this narrower region up here in the first box, and with 95% confidence, we believe P could fall within this region. Again, so we're moving from sample proportions to trying to infer what the true population proportion would be from that. Okay, so let's leave it right there for now. Obviously, well, no, one thing I should note for you again here. As the confidence goes up, the interval increases in size as well. So with 95% confidence, the accuracy of our prediction drops. With 68% confidence, the accuracy goes up, but we're less likely, how to say that? We're less likely for P to fall within that boundary. We've got a smaller gap that the true population proportion could actually lie within. All right. On this slide, you've got a representation for how to think about confidence. Last slide, we talked about 68% confidence, about 95% confidence. All these little dots here, pointing them out for you, those are representing what a sample proportion of 1,012 adults would believe in terms of ghosts, whether or not they exist. Let's say, so we've got this weird graph set up. This horizontal line right here represents the true population proportion of all U.S. adults who believe in ghosts. Let's just say hypothetically, I just made this up, I don't know what it is. Let's say it's 0.37. If we say that we have 68% confidence, then what we mean by that is that essentially, or approximately 2/3, 68% being just over 2/3, of all samples, that should be a W, would contain P. the true population proportion of people who believe in ghosts. So at 95% confidence, that leads us to 19 out of 20 of all samples would contain P. Okay, so this visual that you've got up above, those red dots again represent the sample proportion that you could obtain if you wanted to get samples of size 1012 over and over and over again. And sometimes, like you have right here, you're obviously going to miss the mark. If you're reporting a 68% confidence interval or a 95% confidence interval, sometimes the net that you're casting within the bell curve doesn't actually contain P. That's normal, that's expected. That's why we say we fudge twice. When we're trying to get P, the true population proportion of success, we fudge twice in that we report a confidence, that is, we're not being certain that P falls within the interval. There's our first fudge, and then the second fudge is that we're not saying what we think P truly is, only that it lies within some interval. So confidence intervals are a little strange in that sense. Our predictions can't be highly accurate. We've got to admit that samples can be off, like that blue arrow sample shows you there, and we've also got to report an interval within which P could lie, not a specific value. All right. We are closing in on being done with these notes. I want to introduce sort of the theory, and we'll talk about problems in class together. What I want to do in example 2 here, and this is going to wrap it up for us, is this. Let's talk about whether or not, based upon the context given to us, these 5 conclusions A through E are fair to make, based upon what little bit of theory we've seen so far. So we're told a catalog sales company promises to deliver orders placed on the internet within 3 days. Follow-up calls to a few randomly selected customers show that a 95% confidence interval for the proportion of all orders that arrive on time is 88% plus or minus 6%. Are the conclusions below correct? And we want to explain. So, the first conclusion that they want to make based upon the fact that they gave us this confidence interval right here with 95% confidence is that between 82% and 94% of all orders arrive on time. No, that's not fair. Because that's a definitive conclusion that interval 82 to 94%, which is just 88% plus or minus 6%, does indeed contain P. We can't know that. This is certain of the accuracy of our interval. So it's sort of ignoring the first fudge that we have to make with the confidence interval, and that is report to with what confidence we believe the interval does contain P. Okay, second thing here, 95% of all random samples of customers will show that 88% of orders arrive on time. No, that's ludicrous, because obviously from sample to sample of where they're, let's see, they didn't give out a sample size here, with these customers will behave differently. To say that 95% of all the samples are going to similarly show 88% of the orders arrive on time is something we can't know. We can't know how other samples are really going to behave. How other samples might behave. At least I should clarify. At least to this accuracy. We could do so with an interval like we did last chapter, but we can't say, oh, 95% are going to have 88% on time. All right. See here, 95% of all random samples of customers will show that 82 to 94% of orders arrive on time. Okay. This one, a little bit tricky. 25% of all random samples of customers will show that. Oh, no. Okay, so obviously, so this is faulty in that they're saying 19 out of every 20 samples is going to have a similar confidence interval. That's not true. Look back to last slide with me. We expect from these little bars that we have represented here with those dots in the middle that samples are going to behave differently. People are different. Things are different. They're not going to behave uniformly. So, also not a fair conclusion. Samples are sure to vary widely. We can't know that they're all going to have that same confidence interval underlined there. All right, D. We are 95% sure that between 82% and 94% of the orders placed by the customers in the sample arrived on time. Well, we're 100% sure of that. That doesn't make sense. They're talking exclusively about the sample. We know with 100% certainty that 88% of the orders arrived on time. So, no, we know with 100% certainty orders arrived on time 88% of the time for 88% of the customers. All right, finally here, can we conclude that on 95% of the days between 82% and 94% of the orders will arrive on time? Also, not fair. Our sample did not deal with the days of delivery. We were talking strictly about orders arriving on time for customers through this internet business. So, no. Our sample said nothing of timeliness with respect to days. Got to be careful with your conclusions. What can we know? What can we say? Well, I would stick to the stats lingo here. Excuse me. On the AP exam, the best thing you could say is what they say in this second sentence here. Let me double check. Follow-up calls to a few randomly selected customers show that a 95% confidence interval for the proportion of all orders that arrive on time is 88% plus or minus 6%. That's as much as we can know. So with 95% confidence, we believe that the true proportion of internet orders that are that are delivered on time for customers falls within 82% and 94%. That's as good as we can get. All these other conclusions are going off the mark. Anyway, there's the end of the video. Kind of short, very different. I will see you guys next time.